Sushruta for NEET is now available on the Google Play Store. Try it out for free.
Good afternoon, students, or good morning, students. So I thought I will get started. The important points that we are looking to teach here today is to have students be able to solve problems dealing with gravitation. So before I get down to it, let me go ahead and share my screen. This today I'm going to focus exclusively on gravitation, and I'm going to mainly focus on problems. But before we go there, I want to outline the Independence Day special. This is a very special program, very limited time. If you miss it, you miss it, and you have to go back to paying the full price. Now, the Independence Day special goes for 39.95 for 6 months or 59.95 for the full year. And when we say full year, we mean till the next set of JEE exams finish, which is about in August or so of 2022. So JEE and NEET exam. So NEET is September this year. I don't know next year when it will be. I assume it will be June, July, but it will go till that time. But if you wanted to keep it for 1 or 2 more months, whichever is later, the 1 year is later than that, then you can keep it till that time. So it's a 1 year program, and so at 39.95 you get the full cell phone app and all the resources that come with it. And right now we have a wonderful self-assessment module. And you will get that if you pay 59.95. You will get that for a whole year. This is probably the best program in the market for both JEE and for NEET. So please avail this program. This is going to be there only for 1 more week, and in 1 week we will take it off and we will go back to full pricing. So be very careful there. Okay. So I'm now going to get on with the program. So a planet, basically Kepler's laws form the foundations of what is gravitation. But there are 2 more very important laws. One is Newton's law of gravitation, and the other is the laws dealing with energy. That is total energy in a conservative field is conserved. Right? So potential plus kinetic is conserved, and the work energy theorem. So these are all the broad set of results that you should know for gravitation. So Kepler's first law: every planet circles the sun in an elliptical orbit, and that is true for any moon, any satellite, etc. Any case where there is gravity and there is an orbital action that takes place. Right? Now, we all know that on top of that, there is the second law, which states that the dA by dt is a constant, or the aerial velocity is a constant, and we know that results from conservation of angular momentum, or I omega is a constant, or r cross mv is a constant. Right? The third law states that t square is proportional to r cubed. The period of a planet is proportional to the cube of the semi-major axis, right? T square is proportional to r cube, and we told to explain to you how that is derived, right? So then we looked at several problems, but today I'm going to look at some more problems. But the other important rule is, of course, Newton's famous law of gravitation: G m1 m2 by r square is equal to the force of attraction between any 2 masses m1 and m2 separated by distances r. Right? So, and it's true for any and every pair of masses, right? And therefore, using this, if you set gmm by r square equals m omega square r, right? and you write omega equals 2 pi by t, you will end up with t square is proportional to r cubed, right? And you will get you will end up with a constant, right? So so t square is proportional to r cubed, right? And then you of course need to know what you learned in uniform circular motion, which is where you get your mv square by r, right? So now let's look at we looked at this problem last time, but I'll look at it one more time. The elliptical orbital orbit of a comet is shown above. Positions 1 and 2 are the furthest and the nearest. Okay, the distance to the sun. As you know, comets have almost like a cigar-shaped orbit, right? And at position 1, the distance for the comet to the sun is 10 times that as position 2. Okay, so at position 1, at position 2, the comet's kinetic energy is, well, you all know that kinetic energy is changing because the velocity is changing. So what is constant, right? Mr square omega is constant, right? Or m times v times r is a constant, right? So if m times v times r is a constant, if r1 divided by r2 is 10, right? Then v2 divided by v1 is also 10. So v squared divided by v1 square divided by v2 square will be changing, right? So the comet's kinetic energy is, there is total energy conservation, right? Therefore, the comet's kinetic energy is maximum at 2, right? It's going to be moving the fastest at 2 because v times r is a constant. So 10 times faster at 2 compared to at 1, right? So mvr is a constant, right? So r cross mv is the kinetic, is the angular momentum. Angular momentum is conserved, right? So the kinetic energy is going to be the greatest at its maximum value for the orbit c, right? Comet's kinetic energy at 2 is going to be maximum value of the orbit because it's the closest position, right? Because it's the nearest position. What is the ratio v1 by v2 of the speed? That we already said, right? R cross mv is constant, r times v is constant. Therefore, if if the speed of the comet, right? So because of that, rv is kept constant. Therefore, v1 by v2 equals r2 by r1, right? v1 by v2 equals r2 by r1. R cross mv is a constant, right? So r2 by r1 is 10. No, r2 by r1 is 1 by 10, right? Right? 2 is 1/10 the distance from 1, right? So r2 by r1 is therefore 1/10, right? So what is the ratio of the force, right? The force is proportional to at position 1 to the force at position 2, gmm by r square. That is very straightforward, right? The masses are the same, so the force is going to be 100 at 2, right? So the force on the comet F1 is going to be 100th of F2, right? So this kind of a question, I took this question so that this gives you a mix of all the ideas that you deal with, right? And so you are able to parse around and move around the various ideas. Then I discussed this, right? So in this case, the gravitation inside the earth, it is a straight line. As you go inside the earth, at the center of the earth, the gravitation is 0, right? And as you go to the surface, it becomes the highest. The surface of the earth, assuming it's a full sphere, it is at its highest. And then from there on, it kind of goes through this what do you call it? 1 by r square curve. This part of the curve is a 1 by r square curve, right? And then at this point, we said that, if you make this a straight line, near the surface of the Earth, if you make it a straight line, right, we normally assume it's a constant, right? Because the small distances over that, it does not change that much, right? So it is G naught, right? Normally when we do MGH, right, we mean that it stays constant over some small height, right? But let's say the height is not that big compared to the radius of the Earth, right? But it's little bit big, okay? So it's not the same as the surface of the Earth. Maybe it's like Mount Everest, that kind of thing, right? So, or if an aircraft is in the air, right? So in such situations, then for this line, this can be approximated as a straight line, right? At this point, if you go for much further, of course, it's a curve, right? It should be an r square, 1 over r square relationship, right? This is like this, right? 1 over r square, right? So now, but just right here, right? It can be approximated, say, straight line, G naught minus 2h by r G naught times G naught, okay? 2h by r, 1 minus 2h by r, the whole thing times G naught. So there's a product there. Here is a star G naught there, 2h G naught by r, okay? So only then the units will match, right? So G naught times 1 minus 2h by r, okay? So that's this one, this formula, right? So this is G naught, GMM by r square is G naught, 1 minus 2h by r, okay? So now the variation of the value of G above the Earth is G goes down linearly, right? When we go inside the Earth like that, it goes also down, but that goes when you go up, it goes down at twice the rate as when you go inside small distances. Let's say you dig a deep enough hole, right? Then what will be the G, right? So that's as far as that, right? Okay, all right. So the total energy, as you know, it's a conservative force. Gravity is a conservative force, and because it's a conservative force, the work done is independent of the path, right? Therefore, half mv square plus V of r, where V of r is the potential energy, is a constant. Ke plus P, total energy, is a constant. Like in the case of electrical field, gravitational potential, V at a distance x, Vx minus V infinity. Sometimes we say V infinity is 0. And then therefore you have a negative potential energy. Right? All right. Okay. So Ke plus P is a constant, half mv square plus gmm by r, or minus gmm by r is a constant. Okay. So now when a satellite is in orbit, right, you have 2 pi r by t, right? What is t? T is let's say it's a circular orbit, it goes down once, right? So that is, and if there is a radius a, it is, or if it is a rough ellipse, right? You take the semi-major, right? If it's an ellipse, major axis, minor axis, a plus b by 2, right? And therefore 2 pi r a by t. A is the semi-major axis, x1 plus x2 by 2, right? So approximately velocity will be 2 pi r divided by the period of the planet or the satellite. Okay, so now that is also equal to root of gm by a, where a is the distance from the center of the Earth. Okay, root of gm by r is the orbital velocity. Thus, we end up with an equation to calculate the new total. So the total energy is half mv square plus gmm by a. That's the total energy rocket to reach this new energy, right? So now we then introduce this idea called escape velocity. Escape velocity is the velocity to be given to a body at its current location so that it leaves the gravitational field of the planet or whatever body that it's revolving around, right? So if a body is pushed upwards from the earth, it can go up and then come back down, right? So if you throw a ball, it just comes back right back at you, right? Falls on your head, right? Now, some bodies, if you throw them far enough and you give them a little bit of horizontal velocity, then they go into the orbit, right? That is, you're giving it orbital velocity. Now, you can also give it so much energy that it escapes the gravitational field of the body, right? So, how much energy should you give? Equivalent to the potential energy, the gravitational potential energy. Your total energy should exceed the gravitational potential energy. And so, what is the escape velocity? It is, we already said, gm by square root of gm by r is the orbital velocity, square root of gm by r, right? So this one is twice that. You add another root 2 to that. That is called the escape velocity. So root 2 times the orbital velocity will give you the escape velocity. This is what it takes to leave the Earth's gravitational field. Note that here m is for the Earth, right? If it was a different body, it will be that body is m, right? G, as you know, is a universal constant, right? And r is the distance from to the center of that body. Okay, so that is the escape velocity, square root of 2 gm by r. So if there's a root 2 beyond, this is just gm by r, that this one is square root of 2 gm by r. Assuming a satellite is orbiting the Earth at a height h above the Earth, gm by r square equals mv square by r, right? That's how most cases you end up with. That's how you end up with t square is proportional to r cubed. This is t square is proportional to r cubed. Okay, so this is the formula you use at a height h. What will be? How do you find the period at any height h? The period will be given by this. T is equal to using gm by r square mv square by r. That's how you calculate the period. T square is proportional to r cubed also comes from that, right? So now at that height, what is the PE? gmm by r or gm by r plus h. What is the KE? Half mv square. What is the total energy? P plus KE, right? So, and that's how we calculated this one, right? So notice that as you go further and further away, your potential energy becomes lower and lower. What do we mean by that, right? It should be higher and higher, right? So it, right, because if you are sitting on the Earth's surface, potential energy should be the least, right? So as you go up and up and up, it should go higher and higher and higher, right? So why is that, right? gmm by r, but actually you're saying it goes, because by convention it has to be negative. Okay, so that's how you end up with that. So you have to be a little careful with that. Okay, so by convention it is negative gm by r. Okay, so gravitation, and when you take the derivative, that's how you take the derivative as well, right? So what is v infinity, right? So at v infinity, you in fact you have to impart so much energy and to give it that extra potential energy, right? So in a way, this is a very tricky idea, this potential energy. Okay, it is a convention. Okay, a satellite is moving with a constant velocity v in a circular orbit. Object of mass m is ejected from the satellite such that it just escapes from the Earth's pull. At the time of its injection, the kinetic energy of the object is, gravitational potential energy is what, right? gmm by r, right? So gmm by r should equal, if you gave it as much energy, what is the current kinetic energy? Half mv square, right? You must give twice that in order for it to escape. You must give twice that for it to escape. Okay, so Now the total kinetic energy needed to escape the Earth is the gravitational energy. Therefore, the Ke that needs to be given is mv square. So its current kinetic energy is half mv square. You must give it an mv square in order to escape the Earth's field. Right? So K plus U equals 0. If you assume that equation, that's where this comes from. Okay? K plus K is equal to negative U. And therefore, K is mv square. All right. So acceleration due to gravity. Okay. The height at which the acceleration due to gravity becomes g by 9 in terms of r, the radius of the Earth is, right. So in such cases, you cannot use negative 1 minus 2h by r because there is a massive change in the gravity, right? Now you must use g by r plus h, the whole square equals g by r square. Okay, so that is what you should not get confused by the theory here. So you should just use g by r plus h, the whole square equals right. Equals gmm by r plus h, the whole square, which is going to be the new acceleration due to gravity, right? And therefore, the g nu is going to be g times r by r plus h, the whole square, right? So it is going to go down as you go further and further up, right? And that's proportional to r by r square, right? So at a height h, it's good. The new g is g by 9, right? So the g and g cancel. Therefore, r plus h square equals 9r square. Therefore, when you solve that, you have r plus h equals 3r. So h equals 2r. Okay. Now, if you used the linear form, you will get the answer wrong because 1/9 is too big. Okay. It's normally the linear portion is going to be like maybe 5-10%, and there's a 5 to 10% difference. This linear portion, right? This formula 1 minus 2h by r, this formula, right? That is only for heights which are small compared to where h by r is small, like 5%, 10%. H is maybe 5% above the Earth, something like that. Okay, so keep that in mind when you solve these problems. Okay, so now a binary star system consists of two A and B which have periods Ta and Tb, right? So in this case, right, what can you say? You can say that consists of two stars A and B which have time periods A and B, right? So in this case, the angular momentum is conserved, right? So what does that mean? Mr square omega 1 equals Mr square omega 2, right? Radii is Ra and Rb, right? So Mr square, Mra square, R1 square omega square equals Mr2 square omega 2 square, right? But then M is different, A is different, right? So there are so many moving parts here. Okay, in a binary star system, they're not twin stars. One could be bigger, other could be smaller. One could have bigger mass, other could be smaller mass, but they are revolving around each other, right? And therefore, you cannot say too much in such cases. Okay, so are the periods? Will the periods be same? Right? If TA is greater than TB, then RA is greater than RB. Well, you can say T square will be proportional to R cubed, right? T square will be proportional to R cubed, but that is true only when the masses are the same. Masses are not same, right? So the only thing you can say is Mr square omega will be the same, right? And so now, TA equals TB, none of these things are really true, in reality, So anyway, so let's go of that problem. You really cannot say any of those choices. Satellite S is moving in an elliptical orbit around the Earth. The mass of the satellite is very small compared to the Earth. The acceleration of S is always directed towards the center of the Earth. Very straightforward. That is definitely true, right? GMM by R square, A attracts B, B attracts A. The acceleration is in the direction of the force, right? F equals ma. F and A are always the same direction. The angular moment of S above the Earth changes in direction, but its magnitude remains constant. No, the angular momentum is conserved. Total mechanical energy of S varies periodically with time. No, it need not vary periodically with time, right? It's not a simple harmonic motion. The linear momentum of S remains constant in magnitude. No, the velocity keeps changing. Therefore, if it's in an elliptical orbit, the velocity keeps changing. The angular momentum is only constant in magnitude. The angle B is not true because the angular momentum doesn't change direction. It stays. It's both the direction and the magnitude are conserved. Only A is true. Okay. So now let's look at this one. Choose the correct alternative. Acceleration due to gravity increases with increasing altitude. No, it decreases with increasing altitude. We already saw that graph. Acceleration due to gravity increases with increasing depth. No, decreases with increasing depth also, right? Acceleration due to gravity is independent of the mass of the Earth / mass of the body. It is independent not of the Earth, but of the body. It is not independent of the mass of the Earth. If you had a smaller Earth, a lighter Earth, you will have less gravity, right? The formula negative GMM by times 1 minus R1 is less accurate than the formula mg times is more accurate, right? NGH is a very approximate formula. We already discussed that. So this question is really targeted so that you understand this slide. These 3 slides. Okay? This is really to help you understand these 3 slides. Okay? So suppose there existed a planet that went around the sun twice as fast as the Earth. So its period is half. If the Earth's period is 24 hours, its period was 12 hours, right? What would be the orbital size? T square is proportional to R cubed, right? What would be the orbital size if T is halved, right? What will be the corresponding R, right? If T becomes T by 2, right? Then what will happen to the R, right? The T's will cancel, therefore the R's will become root 2 will become what will be the orbital size? Be closer, right? Shorter, right? So root 2 times 1/3, right? So 1 by root 2 times 1/3, right? So 1 by root 2 times 1/3 is how much? So root 2 is 1.414. So 1 by 1.414 is 0.717, right? So it is the cube root of that. So it will be little more than 0.8, 0.9, somewhere there. Okay. So that will be so 1 by root 2 times so that is what you have to do. T square is proportional to R cubed. Okay. So use that to arrive at the result. So T to the power of so if the T has become half, right? So it will become 1 by 2, right? So 1 by 2 to the power of 1 by 3, right? So that will be the R. There you go. Okay. So now a satellite is moving around the Earth in a circular orbit. Following statements are given. Is moving with constant velocity. Is that true? It suffers no acceleration. Is that true? Its angular moment with respect to the Earth remains conserved. Its distance from center must be equal to root 2 times the radius of the Earth. All right. So it is moving with a constant velocity. You must always be very careful with such questions. It is moving with constant speed, but not velocity. It suffers no acceleration. No, it has acceleration. mv square by r is happening, right? V is always tangential. The velocity is always changing because its direction is changing. The speed only is constant. Its angular velocity with respect to the Earth remains conserved. That is true. Okay, its distance from the center it has to be root 2 times radius of the Earth. No, it can have any distance from the center of the Earth. It need not be root 2 times radius of the Earth, right? This might be for if it is a geostationary satellite. Not every satellite. They haven't said anything about geostationary. So only 3 is true. Okay, a small ball of mass m is released at a height r above the Earth's surface. R is the radius, right? The maximum depth of the ball to which it goes is r by 2 inside the Earth through a narrow groove before coming to rest momentarily. Okay, the groove contains an ideal spring constant k and natural length r. The value of k if r is the radius of the Earth. See, these kinds of experiments will never happen, as you may have guessed, but they like to ask such questions. So they think with questions in mind, so they come up with such questions. So now the groove contains an ideal spring. The value of k if r is the radius of the right, and the natural length r. The value of k if r is the radius of the Earth and m is the mass of the Earth is how can you say what the k is, right? The maximum depth of the ball to which it will go is k r by 2. Okay, so that's what he's saying. So at that point when it goes to r by 2, right, you have f equals kx. So k times r by 2, so it's compressed at r by 2, f equals kx. So k times r by 2 equals the gravity at this point, right? So the gravity at this point is gmm by r square, right? So gravity at r by 2 is gmm by r square by 2 because it's a linear straight line, right? So gmm by r square by 2, right? Gm by r square by 2 equals k times r by 2. Okay, so because they have introduced all this 3 and 9 and 6, right? So, but that's all you have to do, right? You have to, how much will it compress? It will compress as much as the up to the point where f kx equals gm by r square. Okay, and so the answer to this one is supposed to be none of the above. Okay, but that's what you have to do. Gm by r square equals kx. The fractional change in the value of free fall gravity for a particle when it is lifted from the surface to an elevation h, where h is far, far less than r, is change in the value of gravity will decrease. And by how much? You know this. Minus 2h by r d. Okay. So these are all related to that slide that you have, right? A satellite is revolving around the Earth at a height h. Satellite explodes into two equal parts. One part has zero velocity after the explosion. Okay, so one time half mv square. Now the full half mv square is now gone on to the other body. right? Now, and the other moves in the same direction with double the orbital speed. So now its original orbital speed was what? Gm by r. So now it has become or square root of Gm by r, right? So v was orbital speed is v equals root of Gm by r, right? So now it is 2 times that. Okay. Now if it is 2 times that, the maximum velocity reached, the maximum height reached by the with double the velocity is what? Well, here's the thing. It's you know, it's more than square root of 2 Gm by r. Okay. If it is more than square root of 2 Gm by r, then it is more than the escape velocity. So it's going to keep being able to go forever and forever and forever. So it's going to have escape velocity. That's the point here. They are trying to see if you understand what whether it's beyond the threshold of escape velocity. Then it's not going to go to some maximum height and come back. It's no longer under the it has escaped the gravitational field of this particular of the Earth. Okay, so it is none of the above. Okay, if the radius of the Earth were to shrink by 1%, its mass remaining the same, the acceleration due to gravity on the Earth's surface. So the radius declines, right? But the mass stays the same. The acceleration due to gravity on the Earth's surface would so g m by r square is acceleration due to gravity, right? So now they are saying m is the same, r square now declines, right? So if r square declines, gravity is going to increase, right? All right. So maybe I don't know if you want to look at this free response question. I think you may want to do it. Let's take a look at it. Okay, a toy rocket of mass 0.5 kg starts from rest on the ground and is launched upward, experiencing a vertical net force. So take this. This is a free response question given to the American students, but take this as something maybe that you may see in, say, a JEE Advanced. Okay, but usually the free response questions are a little easier than JEE Advanced, but still it's worth a try. Okay, a toy rocket of mass 0.5 kg, but sometimes they can get tricky. It starts from rest on the Earth's surface and launch upward, experiencing a vertical net force. The rocket's upward acceleration, A, for the first 6 seconds, A equals K minus L by L times T square, where K is equal to this much and L is equal to that much, 9 and 0.25, right? At T equals 6, so what happens at T equals 6? What happens to this equation? 9 minus 0.25 times 36. So 9 minus 9, A becomes 0, right? So at T equals 6, fuel is exhausted and the rocket is under the influence of gravity alone, right? So the rocket's upward acceleration then becomes 0, right? At that point, right? Now assume the air resistance in the rocket's change in mass are negligible. Calculate the magnitude of the net impulse exerted on the rocket from T equals 0 to T equals 6, right? So 0.5 times K minus LT square, right, is what is the net impulse? Impulse is F dt, integral F dt. F is equal to dmv by dt, delta mv. The change in the momentum is the impulse, and that is equal to integral F dt. That's what they want you to do. 0.5 times K minus LT square dt. Integrate that from 0 to 6. Okay, so that will give you A. Calculate the speed of the rocket at t equals 6. Okay, this is a little bit trickier. So dv by dt equals k minus lt square. So v, right? So the rocket starts from rest, right? So v equals integral k minus lt square dt 0 to 6, right? So that will give you the result of that integral will give you the speed of the rocket at t equals 6. That is B. Okay. Calculate the kinetic energy of the rocket at t equals 6. Once you got the speed, just do half mv square. Calculate the change in the potential energy of the rocket Earth system from t equals 0 to t equals 6. Okay. So that you can do gmm by r square, right? And because it is continuously gaining potential energy, right? So gmm by r square. So you calculate the distance traveled. How do you calculate the distance traveled? You write dv by dt, right? Equals dv by ds times ds by dt. Therefore, v dv equals so one has to use something like that, so calculate the change in gravitational potential energy, right? So you want to know how far it will go first, right? So the change in the potential energy is a function of position, right? So that's why you're trying to calculate how far it will go, right? So dv by dt equals k minus lt square, right? So dv by ds times ds by dt, right? So v dv will give you k minus lt square, right? Now, what you should do is you already calculated the speed in b, right? When you did the integral, you calculated the speed v, right? V as a function of t, right? So v will equal what? V is equal to kt minus lt t cubed by 3, right? So now, um, um, that is not so straightforward, right? So, V is written in that form, and then you do one more integrals with that, right? That's the other way to do it. So S will equal kt squared by 2 minus lt to the power of 4 by 12. Okay, so you reintegrate what you integrated in B, right? So that will give you the distance. Okay, that's what you need. So calculate the change in the gravitational potential energy from t equals 0, t equals 6. Initially, it is m times g times h. Finally, also it is m times g times h. Okay, so that will give you, once you've calculated the distance traveled, that will give you the new mgh. Okay, so the change will, so that will give you the total mgh, and using that you can calculate the change, the gravitational potential energy. Calculate the maximum height reached by the rocket relative to its launching point. Okay, so now you calculate the kinetic energy of the rocket at t equals 6 and the position at t equals this, right? Now, from here on, right, what is going to happen? All the kinetic energy gained here is going to get converted to potential energy. So there is an mgh that's traveled after 6 seconds. So from here, all the half mv square that it has at this position is going to get converted to potential energy, at which point it will come to rest somewhere in space, right? So the answer in C1 equals mgh. Okay, so you take that h and you add that to the h you calculated in C2. So the h from this plus the h from this will give you the total h. So that will give you D. Okay, so really on the axis below, assuming the upward direction to be positive, right? Sketch a graph of the velocity v of the rocket as a function of time. That is just when you integrate this kt minus lt cubed. As time goes, right, its velocity is going to go like this, but at some point it's going to uh, keep reaching. Eventually the slope is going to go to 0. Okay, so it's going to be something like this. Initially maybe it's going to cut over, right, and then it's going to go to 0. The slope of the v versus t curve is the acceleration, and that acceleration is k minus lt square, right? So it goes to 0 at some point. Okay, so initially at t equals 0, what is it? It is 9. So initially it's 9 and then it goes to 0, right? So it's going to be something like that. Okay, so those would be all the parts to that free response question. Okay, so you have to use all the tricks that you have learned so far. See, is they have solved using that, and they reintegrate t square plus t to the power of 4, right? And then they evaluate substitute that in order to gain the potential energy. Okay, so the point of solving this is to understand that the axis above, assuming so he has got it goes up and then it comes down. I was wrong. So it goes up and then it comes down and it hits 0, right? So this is a k minus lt square. So he's saying k minus lt square is like this. So yeah, that's true. So the velocity keeps increasing. It's not decreasing. The velocity is not decreasing, it's increasing. So it's going to go up and up and up till it reaches a plateau, right? So it's not going to be decreasing like this. It's going to be increasing. Velocity keeps on increasing till it hits 0. Then it drops linearly. Okay, so I was wrong there. Okay, so that is a very good question, but that comes if you don't think fast enough. Okay, so or you don't pay enough attention. So it goes up, then it drops in a straight line. Okay, so so with that, I will stop for today, and we will continue next week for class 11 with a slightly different topic. I will start, the next topic, possibly simple harmonic motion, and then we will look to continue our discussions with simple harmonic motion starting next week. But in the meanwhile, what I suggest students do is you start working very hard with the problem solving, right? So the more problems you do, the better off you are. Okay, there are a lot of very good problems that you can get. If you buy our app, now we have the self-assessment module. You can use that to get hold of a lot of problems. The self-assessment module will really help you solve a lot of problems. Okay, and you have to learn to attempt and ready yourself for all the difficult problems that show up in all these exams. Okay, and make sure that that when you face the exam in the exam hall, you are not caught napping at that time. Now, till then, you're fighting. Every day you're fighting, you're learning a little more, you're improving your abilities, right? And see, physics is not that easier subject. Okay, physics is easier when you solve a lot of questions. You build a lot of expertise, you learn a lot of the material well, then and you solve more problems, then over a period of time you will understand how to solve various types of problems. You will build expertise, and most importantly, you will be able to read a question carefully. Okay, solving a lot of problems readies you for the tricks that show up, and readies you to think little more analytically, and to be able to exercise all parts of your brain and be alert when you attempt questions. So that was the aim of today's class. It is to get you all understanding that even though gravitation has only so many concepts, right? It's not like 500 different concepts. It has only so many concepts, but there are so many variations of questions that they can ask you. But it involves a wide range of ideas that come into play when you solve any set of questions. So it is an application of various parts of what you learn in kinematics, mechanics, energy, angular momentum, and rolling, all come in the build-up that comes into gravitation. Okay, so with that, I'm going to conclude. And next class, we will go to simple harmonic motion, and then we will go and do a little bit of waves. Then we will do stress and strain, etc. And then so that we can kind of have done all parts of mechanics, before we get started. Meanwhile, as you know, tomorrow we have our electricity and magnetism. We are going to wind down current electricity. So attend that lecture. We will be discussing Wheatstone bridge, etc. So we are aiming to take all you students along with us. But for that, you have to make an effort as much as we do. All right. Thank you very much.